To test the facts and fully demonstrate how differently thermosets and thermoplastics behave when exposed to heat, we carried out a series of indicative ISO 5660 Part 1 tests. ISO 5660 Part 1 specifies a method for assessing the heat release rate and dynamic smoke production rate of a material. It is otherwise referred to as the cone calorimeter test. In preparation for the test, a 100 by 100 mm test specimen is wrapped in a single layer of foil. The upper surface of the specimen is left exposed. Once placed in the specimen holder, any excess foil above the top surface of the specimen is removed. To ensure the test specimen is not exposed to radiant heat from the cone-shaped radiant heat panel before the test commences, a removable radiation shield is positioned above the test specimen. After 15 seconds, the shield is removed and the igniter is powered. The test duration should be carried out in accordance with section 11.3.5 of the test standard. Now we've covered the test procedure, let's have a look at the indicative tests that we carried out. The first indicative test exposed a specimen of Kingspan Cooltherm K15 rainscreen board, a rigid thermoset phenolic insulation recognised as combustible, to the radiant heat panel. Upon commencement of the test, the heat from the radiant heat panel causes the specimen to undergo pyrolysis. Pyrolysis is the process of thermal decomposition of a combustible material. It happens when the material, which in this case is a specimen of Cooltherm insulation, is subjected to heat energy. In this instance, the pyrolysis results in two products: hot combustible gases, pyrolysis gases, and char. Pyrolysis is an endothermic reaction, meaning it absorbs heat. This pyrolysis results in the black char that is formed on the surface of the board. This pyrolysis also releases combustible gases, which cannot be seen, but the result of their subsequent combustion can, in the additional flames that occur 23 seconds into the test. The additional flames you see are a result of the exothermic reaction, combustion, between the hot combustible gases and oxygen. These additional flames are most obvious in the first 30 seconds of the test, after the radiant heat panel is introduced whilst the initial char is formed. After this, the flames die down a little and the amount of char gradually increases. This char protects the uncharred insulation beneath it from the radiant heat panel and the heat from the combustion of pyrolysis gases, and thus retards the pyrolysis. Whilst the surface of the char keeps undergoing pyrolysis, the rate of emission of pyrolysis gases lessens, and the nature of the pyrolysis gases changes the more pyrolyzed the char becomes. The net effect is that the rate of production of pyrolysis gases and the intensity of the flaming produced by their combustion reduces after the formation of the initial char layer until equilibrium is attained. The energy released from the combustion of the pyrolysis gases provides some of the energy needed to cause further pyrolysis. However, at 3 minutes 5 seconds, when the radiation shield is returned above the specimen to mark the end of the test, the energy from combustion of pyrolysis gases alone is insufficient to support further pyrolysis, and the specimen immediately self-extinguishes. Our second indicative test exposed a specimen of polyethylene beads, a thermoplastic material also recognised as combustible, to the radiant heat panel. As we've previously mentioned, combustible materials undergo pyrolysis when they are subjected to heat. This is as true for polyethylene as it is for phenolic insulation. For polyethylene, a thermoplastic material, the immediate reaction to the heat is to soften and melt. We can see from the video that upon commencement of the test, the radiant heat panel causes the polyethylene specimen to melt. This melting makes char formation impossible, as char can only be formed from solids. Subsequently, the liquid polyethylene undergoes pyrolysis. This pyrolysis releases combustible gases which cannot be seen, but the result of their subsequent combustion can in the flames that occur. The flames you see during the video are a result of the exothermic reaction, combustion, between the hot combustible gases and oxygen. These flames are evident from 1 minute and 5 seconds into the demonstration and become increasingly aggressive after 1 minute and 25 seconds. As pyrolysis of liquid polyethylene does not result in a protective char layer, the rate of emission of combustible pyrolysis gases is maintained and flaming does not die down quickly. These flames continue after the 3-minute test has ended and continue until all of the polyethylene specimen has undergone pyrolysis. This is shown at the end of the video, where you can see the polyethylene specimen is completely thermally decomposed. In a real-life fire scenario, this can cause an increased rate of fire spread. If positioned vertically within a building system, flaming droplets can fall from the material. These can land on other materials and cause secondary fires, precipitating the spread of fire to other parts of the building. So, as a matter of fact, these indicative tests demonstrate that there is a huge range in the burning behaviour of combustible materials.